Log on, tune in, find out. Another good idea from Cambridge.
Take it away.
Thank you. Okay, so first of all, I'll just start by acknowledging Mark Strong, who's doing this as his PhD. Right, so I'll start off with the application. So I'm interested in use of modelling in medical decision making. So the situation we're interested in is we have a healthcare provider with a finite budget who wants to use that budget to buy as much health as possible for their population. And so we need to be thinking not simply how effective a particular treatment is, but what the associated costs are. So by treatment costs, we mean price of the drug, but price of hospital visits, etc. Any sort of cost that a patient would pick up while being treated with a particular drug. So in the UK, we have a organisation called the National Institute for Health and Clinical Excellence, and they will make decisions for some treatments whether or not they can be made available through the healthcare provider, and they make these judgments on the basis of cost effectiveness. So we have different ways of measuring cost effectiveness, and I'll be using a bit later as net benefit. So you basically just combine your efficacy and treatment costs to a single measure, and we can't directly observe cost effectiveness. So we might have clinical trial data for 1 year, but we want to make predictions of costs and benefits over the lifetime of the patient, and we might not even have the cost data directly observed in any case. So people build models to make predictions of what these cost effectivenesses are going to be. And then the discrepancy question, so I had a bit about this already, but these models are never going to be perfect, and so what we're interested in is, can we say anything about how close the model prediction is going to be to reality? Okay, so if we just start with putting discrepancy to one side and think about uncertainty in model inputs. So we've got our computer model, just representing it, the usual sort of y equals f of x, and the idea of a true input can be a bit contentious, but in this case, quite often we're dealing with inputs that are in principle observable. So we'll imagine that they really are, you really could go in theory and learn the true values of your inputs. But we don't know what those things would be, and what we're interested in is what would happen if I was to run my model at the true value of the input. So what's the uncertainty in the output at the corresponding unknown input value? So this is all quite well understood. We would derive a joint distribution for our uncertain inputs, and then, assuming it's not a particularly tractable function, we could use Monte Carlo. So we'd sample from the input distributions, run the code lots of times, and get a sample from our output distribution. And in terms of what's done in the UK, this is actually the preferred option by the regulator. It's not a formal requirement, but it's generally the preferred thing. Except rather confusingly, it's referred to as probabilistic sensitivity analysis, which we tend to use sensitivity analysis to mean something else. But generally, there's quite a lot of effort that goes into thinking quite seriously about what's the uncertainty in the inputs, and then propagating that through the model to get an uncertainty in the output. Okay, now thinking about discrepancy, so we'll introduce Z to represent the real thing that the thing in the real world that we're actually trying to predict. So what's the real true net benefits for our particular treatment? Now, if we've got an imperfect model, then we don't believe that plugging in the true values of the inputs and running it through the code is necessarily going to give us the true value of our target physical quantity that we want to predict. Now the uncertainty propagation that I had on the last slide, all that's doing is quantifying uncertainty about y. What we want to really be doing is quantifying uncertainty about the true physical quantity. So how do we do that? So we'll define our discrepancy, delta, to be the difference between reality and what our model would tell us if we could plug in the true values of the inputs. Now, the problem we've got here is we haven't got any data directly to learn about delta. If we could run an experiment to learn about this discrepancy, then we wouldn't bother with the model in this case. We just use the data directly. So is there anything that we can say about the discrepancy in our model prediction when we don't have experimental data to compare what the model tells you with reality. So how are we going to do this? Well, what about directly eliciting some distribution to represent beliefs about this discrepancy? Can we do that? Now, speaking to modelers, some of the modelers we've discussed this with, they think this is impossible. So how on earth are we going to do that? Well, you could argue that if you have absolutely no idea on what the difference between the reality and the model is, then why should we be using the model in the first place? But in fairness, this is going to be a very difficult thing to do, and I think in this particular application, probably not that useful in any case. I can't really see what the decision makers would make of it. So we're going to take a slightly different tack. We're going to take the perspective of the model developer, and there are two things we're going to try and get a handle on. The first is that if we think about the model structure, there may be different sources of discrepancy, different simplifications or things we've left out. But almost certainly they're not going to be equally important. So can we identify, in some sense, what the most important sources of discrepancy are in a model? And then secondly, can we understand whether there would be any benefit for decision making to build a better model? Is our imperfect model good enough for the decision problem at hand? And so what we're going to be doing is trying to get inside the models a bit and understand where discrepancies are coming up and perhaps incorporate them inside the model. So this is kind of restricting us to perhaps simpler models where we can actually get inside them a bit easier. So way to think about this, so let's start with a model. We've got, let's say, two inputs and an output. And the first thing we might do is try and understand a bit more about the structure of the model and how we get from the inputs to the output. So we might imagine that inside that model we've got different smaller processes being modelled. So we might have, think of this as a little submodel that produces some intermediate quantity y1, a second submodel producing some intermediate quantity y2, and then a third submodel that gives us my final output based on these intermediate quantities. And we could have inputs, the original inputs feeding into that as well. And then what we can now do is think about what possible errors might be in the smaller components of the model. So let's suppose we want to get from our true values of the inputs to reality. Start off with this part of the process, and we might think, okay, we haven't modelled this part of the process perfectly, so we're going to introduce some error, discrepancy, to correct the model output to the corresponding true physical quantity. Likewise here, and so on. So we've got discrepancies on the individual processes within that model that feed through to ultimately give us our overall discrepancy between prediction and reality. So I've spoken about this before at a couple of meetings, and we've got a case study in the paper now. So what we've done is we have a joint distribution for both the inputs and the individual discrepancy terms. So the inputs would be usually fairly well informed by data, but we haven't got any, perhaps haven't got any data to tell us about these things. So this is mostly expert judgment. Although you might have data on some of your processes within the model, but not others. But certainly there's going to be some expert judgment involved in coming up with that distribution. And then we want to understand how important these various terms are. So we thought about using variance-based sensitivity analysis. So if we think about measuring our uncertainty about reality by its variance, what you're doing here is you're calculating, this numerator is the expected reduction in variance if you were to learn the true value of a particular parameter. So what's the expected reduction in my variance if I learn what are my discrepancy terms? And then the sort of story that you might get out of this is you might find that you perhaps have a particular process that you don't think you've modelled very carefully. So you might have quite a large discrepancy here, but you might then discover that this term is actually driven by what's going on down here. So you might find you have large discrepancies within the model that aren't necessarily very important because you've got other things, other processes that dominate. So if you wanted to think about improving your model, this might guide you into understanding where you should be concentrating your effort into best reducing your uncertainty. Okay, so take a slightly different tack. We're going to think more about the decision problem now. And what we want to try and do is understand our decision uncertainty and whether better models might change the decision or stop us making bad decisions. So same basic idea of trying to put discrepancy terms inside models, but now we're going to use standard decision theory based on expected value perfect information I'll talk about in a moment. So we're going to use, rather than using variance-based sensitivity analysis, we're going to use a decision theoretic sensitivity analysis to understand how discrepancies might contribute to bad decisions. So here's example model I'm going to use. It's quite old, so this is really just for illustration now. But these sorts of models are very common in health economics. They have a Markov model, and the idea is you have different health states, and you have a population of patients who, from period to period, move between the health states. So this is looking at treating HIV patients. We're going to compare two treatments, which I'll just refer to as monotherapy and combination therapy. You put your patient population on one particular course of treatment, and they move around the states, and then different states will accrue different costs. So I think they tend to get more expensive from state 1 to state 3. And then you potentially have different qualities of life attached to the different states. Here we've just got alive or dead. So we've got transition matrices in this model that are uncertain, and then the original analysis, it was assumed that patients can't get better. So if you're in a state, you can only stay where you are or get into a worse state. So you've got a transition matrix for one treatment option, and the way it was set up is that in the other treatment option you just have a single relative risk term that modifies the transition probabilities. So we might imagine that this whole Markov assumption could be a source of discrepancy. We might not believe that these transition probabilities really are staying constant over time. So we're going to try and think about how we put discrepancy into our model. So for each treatment, we have this state vector at each time point, which gives you the proportion of your patients that are going to be in each of those 4 states. So we've got our evolution equation here. So we might imagine that we could add some noise to put error into the model, some discrepancy here, but we think it's almost the same formulation, but it's a bit more intuitive, we think, to think about discrepancy in the transitions. So what is it that's wrong about how you're moving people from state to state? So we've got we're going to have to make judgments about these discrepancy matrices. So it's just a very simple elicitation problem of eliciting a joint distribution for 40 matrices. So that should be quite straightforward. So how are we going to do that? So just writing out my discrepancy matrix here. So we're going to stick to the same assumption that patients can't get better, but it would be straightforward if I wanted to put more discrepancy terms in there. And then in each case, we're going to consider different scenarios and different ways in which the model might be wrong. But basically, we're going to use multivariate normal distributions for jointly model these discrepancies. They're kind of inspired by the sort of Gaussian processes that we're all familiar with. So we might have some sort of trend which says that a particular transition discrepancy is going to move in one direction over time, and then we've got covariance between all the discrepancies which get weaker as you move further apart in time, and then covariances between different discrepancies and different treatment options and so on. So some scenarios that we're going to think of. So perhaps we might believe that probability of death is not constant over time, that's going to increase. So we might, if we imagine a single discrepancy term, we might imagine that we're perhaps underestimating it to start with, and overestimating that probability to start with, and the probability gets larger, so the discrepancy increases over time. We might imagine that we don't believe that the efficacy of the treatment is constant over time. So usually with these models, what you're doing is extrapolating. So to start with, we might believe the model, but we think over time, as time increases, we're more uncertain about how effective the treatment is. So we might have a sort of a reduction in efficacy over time. So these are sort of showing samples from our prior for these discrepancy terms. Okay. I think one of the sort of motivations for the sort of Gaussian process framework is that, although they're all looking quite similar here, but we're not trying to say too much about the specific structure of how the discrepancy evolves. We just want to leave that reasonably flexible. And then our third scenario, which I'm rather less keen on, but this is basically saying, well, something's wrong with the model, but we're not sure what. So we'll just say that in some rather unstructured way, these transition probabilities are changing. We just don't know how. But I think I'm a little bit less keen about this. I think it's important to have a good story behind why you think there are errors in the model. So what we want to do now is, having specified these discrepancy distributions, we want to have some way of understanding whether or not they matter for decision making. So I'm just going to sort of review some standard decision theory here. So let's suppose we've got a model with some uncertain inputs, and what we want to measure is how important any particular uncertain input is. Okay? And important in the sense of, would it be worth finding out the true value of that parameter before you made your decision? So we need a utility function to do this. So we're going to suppose that we've got some utility function that will depend on the decision we make and the outputs from our computer model. So in the health economic application, we've got that automatically. In fact, the model outputs are themselves utilities for the decision maker. So if we decide to go ahead and make a decision now, we maximise our expected utility, and then we work out what that's going to be for our optimum decision. So we think of that as our baseline utility. Alternatively, we could learn the value of that parameter before we make the decision. So what we're doing here is we're saying, let's suppose I know the value of my input. What would be my maximum expected utility if I knew that value? Okay. But I don't yet know what I'm going to discover. I haven't actually gone out and found out what that value is. So I have to take my expectation over all the possible values that I might discover, and then I see how that utility compares with what I would have got under the baseline. So this is what Steve was talking about yesterday, the input uncertainty discussion. It's the expected value of perfect information. And in fact, you can, if you want to, rather than thinking about learning inputs, you can think about learning data to reduce uncertainty rather than eliminate uncertainty. It's the same idea. So the way this works, let's suppose we're looking at a particular input. So for the moment, imagine that I fix my input xi at some particular value. So let's say I fix it at 0.1. What I would then do is run my computer model, averaging over all the other uncertain quantities. So I might find that for my first decision I get an expected utility here, and for my second decision I get an expected utility here. And then we're seeing how that conditional expected utility changes as you change the input. So in this scenario, if this is my distribution on that input, my baseline decision would be the blue one, decision 1. And for any plausible value that xi might take, I would still think decision 1, the blue one, is the best decision. It's only out here where I think decision 2 is much better, but I've got no chance of the input taking that value. So this is a case where we've got what we might traditionally call an active input. It is changing the model outputs, but from a decision perspective, it's unimportant, because for any value that you might discover, you make the same decision. So it's not worth learning that before making a decision. Alternatively, if I had a different looking distribution on my input, I might now still think that D1 is the blue one is my baseline best decision. I take the mean of these two curves. But now there's a small possibility that if I was to learn xi, I might get a value out here, and now decision 2 is quite a bit better than decision 1. So to stop myself possibly making a bad decision, it might be worth learning xi before making a decision. So it's got higher value, higher importance. So what we're going to do is, for each of those scenarios, we're going to calculate our partial EVPI for all the discrepancy parameters in a particular scenario and see what's their contribution to my decision uncertainty. So we sort of interpret this as an expected value of improving the model, although it's kind of not strictly accurate in the sense that if you really were to improve the model, that's probably going to bring in perhaps more uncertain inputs. So you wouldn't eliminate the uncertainty, but it's giving you perhaps at least an upper bound on what you might achieve by eliminating a particular sort of discrepancy term in your model. The model I'm working with is actually quite cheap, so you can do this, estimate these quantities using Monte Carlo, but separately I've looked at using emulators to calculate these things if you've got a computationally expensive model. So we can do this for complex models. We could do this for complex models if we had to. So just to clarify the interpretation, when I'm talking about a partial EVPI, it would be the expected value, pounds per patient, of learning a particular group of parameters before you decide which treatment you're going to use for your patient population. The utility we're working with is a net benefit, so it's the, we're going to use an exchange rate lambda of £12,000 times the mean number of years of life you're expected to get on a particular treatment minus the mean cost. I'm just going to choose this for illustration, so I'll actually come back to that in a second. So the sort of things you might get out of it are sort of the following. So if we start with this one, this is where we're pretending that our model is perfect. Okay? So we've kind of got this overall decision uncertainty where we said that if we could learn our inputs, all the inputs, that's got in some sense a value of £365 per patient in terms of, in some sense, avoiding a bad decision. And we can break it down into, would it be worth learning about our uncertain transition probabilities or the relative risks or the uncertain cost parameters, and we find out that these things are important. Okay, then our first scenario, we were thinking that we didn't believe that the risk of death was constant, so we've got structural error there. So what would happen if we put in that discrepancy into the model? Would it be worth reducing it? Well, it does change the overall EVPI and the relative value of some of the other terms, but actually, in this particular scenario, you've got discrepancy, which you don't think is very important. Eliminating that discrepancy is not giving you much value. So we've got a scenario here where you think your model's wrong, but making it better is probably not worthwhile because you wouldn't actually get much value out of improving the model. This scenario, this is where we think that we don't believe that the treatment has a constant effect over time, but we're not sure how to model it. So now the story is changing. Now we're finding that actually it's the uncertainty in the model structure that's kind of the most important in terms of decision uncertainty, and we get less value by putting our efforts into learning about uncertain input parameters. And then our sort of final scenario, which I wasn't so keen on anyway, but I mean, it's kind of obvious really. You put in even more noise, you find that the discrepancy starts to become quite a bit substantially more important relative to your parameter uncertainty. Okay, now this is really just sort of for illustration, just to give you an idea of the sorts of things you might learn. If I was actually doing this for real, we actually tend to work with larger exchange rates, so we put more value per life. And actually what you'd find is that all your partial EVPIs were negligible. So you'd have very little decision uncertainty, even thinking about how the model is real, why the model is wrong. Okay, so just to conclude then, so I think the obvious difficulty with this is going to be making those judgments about the discrepancy. It's always going to be difficult, and there's no sort of skirting that. Or I suppose one option that's quite popular is that distribution assumption, so you can always do that if you want. Perhaps a slightly different way of doing it is you might experiment with trying to understand how much discrepancy you can put in and still tolerate. So how much uncertainty can you have about model structure without it being influential in terms of decision uncertainty or variance space or whatever. So perhaps without having to pin yourself down to a particular choice, you can at least still learn something by a bit of experimenting. And then finally, sort of, I think in the past, personally, certainly I've tended to concentrate on just the uncertainty and sensitivity analyses, but I think it is important that we start to think much more carefully about reality and how good these models really are. In particular, I think agonising over calculating sensitivity measures very accurately for bad models probably is not a good use of our time. I think we have to think sort of beyond simple uncertainty and sensitivity propagation and think about this link to reality. Okay, so that's all for my talk. And then just a quick plug. Some of you here came to the computer models conference that we had in Sheffield last year. That was in deterministic computer models. We're going to do it again next year, so I hope to see as many of you there as possible. In particular, I'd like to encourage stochastic simulation people to come. It was mostly deterministic simulation models last year, but we'd be very keen to get more engagement with the stochastic simulation community. So that'll be running next year in Sheffield. Okay, thank you.
questions for Jeremy?
So how do you contrast your approach with the following in the case of the disease progression model? Actually go build a more complex model where say all of the parameters can be time changing, and then do a decision theoretic sensitivity analysis to the amount by which parameters change over time. How would that be different or the same?
How would it be different to actually building the bigger model, you mean?
Right.
Well, this is something that you can, the idea here is this should actually be a lot less effort than building the more complex model. And if you discover that making the model is more complex is not going to change your decision, or not going to have much value, then I think you've saved yourself quite a lot of effort. And sometimes you might have the best model that you can write down, but you still don't think it's perfect. And you want to know, well, what would happen if we could invest time in research and develop better models without necessarily knowing what they're going to look like.
Henry.
To stop arguing for the next 20 years about whether you use the sort of Bayesian delta discrepancy approach or a more traditional sensitivity analysis, can you kind of formally put the two things, link the two things mathematically together? So maybe one's got a bit more Bayes and the other's a bit more deterministic. Can we actually sit down and write the equations down and leave them mathematically?
I'm not sure what the argument is.
This is Bayesian sensitivity analysis, as opposed to the kind of, you alluded to, a kind of non-Bayesian sensitivity analysis, where you just vary parameters and see what happens.
What you mean, sort of like one at a time approaches, or?
Well, just all the sort of sensitivity analysis has been discussed during this week. Just follow runs, looking input various methods of
what would
uncertainty, modern uncertainty analysis.
I mean, kind of what we've done in the past is we're using exactly the traditional variance-based, for example, sensitivity approach that everyone does, but we're just putting in extra things to represent model uncertainty, discrepancy error. And without doing that, there's, if you only look at inputs, there is no way that you can get a handle on sensitivities to the model structure error. But I don't think there's perhaps quite such the conflict that you might think.
No, I'm trying to minimize.
Do you have some idea, Henry, about how you would incorporate what Jeremy's talking about, model uncertainty into the framework that you were talking about before?
Well, it's an extra layer of Bayesian of parameterization. I mean, it's basically a simple extension to the model to incorporate more parameters. It's very easy to run. That's what the great benefit instead of building on a lot of extra scientific parameters. You put these discrepancy factors. It works extremely well. But what I was thinking is, that simple extensions of models to incorporate discrepancy needs to be combined, I would think, formally with the other forms of uncertainty. I mean, in a sense, it's all inside your head, you know how to do that, but I'm talking about selling that package, that integrated package to the rest of the
I think, in terms of selling it, I think it's a matter of getting on doing it for the moment. I mean, we've already done it in 2 models, in one application area. So Mark and I need to get on and do it, I think.
There's another question over here. Steve?
So in this particular application, you can also be measuring field observations and perhaps looking at mortality and so forth. And some of those parameters might be based on what calendar year it is, in terms of how to measure time. And some of those might be number of years since diagnosis, for example. And so there could be a couple of different ways why there might be some kind of time variation in there. How are you thinking about that time variation? And have you thought about that issue of kind of taking field data and then kind of throwing it back in and learning about, is delta increasing or decreasing or waffling?
Yeah, my guess is that Usually when these models are built, you are extrapolating beyond any data you've got, but you might have data up to a certain point, and you could then start to learn about how your model performs up to that point, and then propagate model error forward from that time point. So yes, I think that's certainly an interesting thing to do when, if you've got the right sort of data to do it.
Any more questions? On the program, it says that there's a discussion from 10:30 to 10:45. I'm wondering if there are any questions for any of the speakers in this session. Or we talked out.